Principles of Bioproduct Separation, Module 2, Filtration and Microfiltration, Segment 3. With me again, Yusuf from Institut Teknologi Bandung. Previously, we have discussed about equipment for conventional filtration and pre-treatment methods in filtration. In this segment, we will discuss about general theory for filtration. General theory for filtration shall discuss three important aspects. First, equations of fluid mechanics related to filtration described as Darcy's law. Second, we shall use the equations to solve for incompressible cakes, which is the simplest case. Third, we will solve problems dealing with compressible cakes, which is the common case in bioseparation. General equations. For a porous bed of solid, Darcy's law relates the flow rate and pressure causing that flow as shown in equation 1, where V is the velocity of the fluid, K is a proportionality constant usually called the Darcy's law permeability of the bed, delta P is the pressure drop, and mu is the viscosity of the liquid. Flow is directly proportional to the potential and inversely proportional to the resistance L per K. However, Darcy's law holds only when the Reynolds number is less than 5. For a batch filtration, the velocity may be rewritten as shown in equation 2, where V is the total volume of the filtrate and T is their time. Resistance L per K may be rewritten to include cake and medium resistance as shown in equation 3, where Rm is the resistance of the filter medium and Rc is the resistance of the accumulated biomass. Combining equation number 1 to equation number 3, we obtained the basic differential equation of filtration at constant pressure drop as shown in equation 4. Medium resistance is a constant independent of the cake. In contrast, cake resistance varies with the filtrate volume, which depends on the compressibility of the cake, which will be discussed in the next slides. For incompressible cake, the cake thickness is directly proportional to the filtrate volume and inversely proportional to the filter area, as shown in equation 5, where alpha represents the specific cake resistance with the dimensions of length per mass, and ρ0 is the mass of cake solid per volume of filtrate. Substitution of equation 5 into equation 4 results a differential equation as shown in equation 6. At t equals to 0, V equals to 0, which means that at the beginning of a filtration, no solution has been filtered. Equation 6 can be easily integrated and rearranged to yield equation number 7, where K equals to mu alpha ρ0 per 2 delta P and beta equals to mu Rm per delta P. Thus, a plot of AT per V versus V per A should be linear. The slope K is a function of pressure drop and properties of the cake represented by alpha and ρ0. The intercept beta should be independent of the properties of the cake, but it is proportional to the medium's resistance, which is often insignificant. The filtration time can be calculated using equation number 10. Compressible cake. Almost all cakes formed of biological materials are compressible and cannot be described with simple analysis discussed as in the previous slide. As these cakes compress, filtration rates drop. The effect of compressibility can be described by assuming that the cake resistance alpha is a function of pressure drop as shown in equation 11, where alpha prime is a constant related largely to the size and shape of the particles forming the cake, as is the cake compressibility, which varies from 0 for a rigid, incompressible cake to near 1 for a highly compressible cake, with a typical value in the range of 0.1 to 0.8. Values of S can be determined by plotting the logarithm of alpha versus the logarithm of delta P. For a high value of S, pre-treatment of the feed with a filter rate is highly recommended. For the next segment, we will discuss about continuous rotary filter. Until then, I am Yusuf from Institute Teknologi Bandung.